Welcome to this deep dive into one of the most common yet misunderstood challenges in data science, multicollinearity. In the transition from classical statistics to modern machine learning, understanding how features interact is not just an academic exercise, it's a necessity for model reliability. We titled this When Variables Fight Each Other, because, as we will see, that is exactly what happens inside your regression models. Let's start with a simple intuition. Imagine you are driving a car, but instead of one steering wheel, there are two. Both drivers are trying to steer the car based on the same GPS signal. If they both move in perfect sync, you can't tell who is actually controlling the car. This is multicollinearity, when two or more independent variables are so highly correlated that the model cannot distinguish their individual effects on the target variable. To understand the mathematics, we must look at the ordinary least squares, or OLS, estimation. The formula for the coefficients is beta equals x transpose x inverse times x transpose y. The problem lies in the x transpose x inverse part. If variables are perfectly correlated, this matrix becomes singular. It has a determinant of 0, and its inverse does not exist. In the real world, near-perfect correlation makes the matrix ill-conditioned, leading to massive swings in your coefficient estimates with tiny changes in data. There are two main types of multicollinearity, structural and data-based. Structural multicollinearity is a byproduct of how we create features, like including both x and x squared in a polynomial regression. Data-based multicollinearity, however, is a property of the population or the sample itself, such as trying to predict a person's weight using both their height in centimeters and their height in inches. How does this affect our results? It doesn't necessarily ruin the model's predictive power as a whole, but it destroys interpretability. The standard errors of the affected coefficients skyrocket. This leads to low t-statistics and high p-values, making you believe a variable is not significant when it actually might be. Your model becomes a black box where the weights are unstable and biologically or economically nonsensical. To detect this infighting between variables, we use several diagnostic tools. The most popular is the Variance Inflation Factor, or VIF. A VIF starts at 1 and has no upper bound. A common rule of thumb is that a VIF above 5 or 10 indicates problematic multicollinearity. We also look at the correlation matrix heatmap to spot pairs of variables that are too close for comfort. Let's look at a real-world example in marketing mix modeling. Suppose a company spends money on TV and radio ads simultaneously every weekend. Because the spending patterns are nearly identical, the model might assign all the credit to TV and none to radio, or vice versa, or give both huge unstable coefficients. This makes it impossible for the CMO to decide where to actually invest the next dollar. Finally, how do we fix it? The simplest way is to drop one of the highly correlated variables. If they carry the same information, you don't need both. Another powerful approach is principal component analysis, or PCA, which transforms correlated variables into a set of uncorrelated components. Lastly, we have regularization techniques like ridge and lasso regression, which add a penalty term to the loss function to keep the coefficients from exploding. In conclusion, multicollinearity is a sign that your data is redundant, while machine learning models like random forests or gradient boosting are more robust to it than linear regression. Understanding these relationships is key to feature engineering and model deployment. Thank you for joining this masterclass. References: Gujarati, D.N., Basic Economics; James W. Titton, H. Hastie, T. Rishbani, An Introduction to Statistical Learning; John E. Friend, Mathematical Statistics.